Understanding the heap. So firstly, what is the heap? The heap is a giant memory region that can be shared in a controlled manner. You can ask the heap for memory and tell the heap when you're done with that memory. Heap implementations are essential system memory managers. So as you must be aware, the C programming language allows you to point at any address in memory, regardless if you can access it or not. This code will compile absolutely fine. If I try to run it, obviously the program will crash. However, when writing a kernel, this code will not crash, because no restriction has been put in place. So as you know, malloc in C returns a memory address that we can write to. It becomes ours for a temporary amount of time. So here, for example, we ask the system for 50 bytes. It returns a memory address, such as this memory address that I've made up, and we can then set that data, 50 bytes worth. When you ask the system for memory, the system also ensures it never gives that memory address to somebody else. Likewise, free in C accepts the memory address that we want to free. It then marks the memory address and all associated blocks as free, and then the next time someone calls malloc, we can safely end up with a previous address that was used. So before we go any further, you must be aware of the memory limits for a 32-bit kernel. Whilst in protected mode, we have certain restrictions because the processor is in a 32-bit state. We are running in a 32-bit mode. We have access only to 32-bit memory addresses, allowing us to address to a maximum of 4.29 gigabyte of RAM. It does not matter how much RAM you have installed in your system. Because we're in a 32-bit kernel, we can only access up to 4 gigabytes. So when you boot up your system, the memory is in an uninitialized state. Your BIOS will start initializing certain pieces of memory and so on. You end up with video memory that takes up portions of RAM, hardware memory that takes up portions of RAM, unused parts of RAM that are available for us to use. So for example, there is an array of uninitialized memory available to us from this address here. This can be a lot of memory available to us or very little, depending on how much installed RAM we have. You should note that this address here is reserved. This means the memory array we have at this address can give us a maximum of 3.22 gigabyte for a machine with 4 gigabyte or higher installed. Attempting to use more memory than this could be problematic. So a heap is essentially a giant piece of memory. That's all it is. So we can point our heap at this address I mentioned here, the uninitialized memory at this address. We can point our heap here. And then assuming you have 4 gigabytes installed, that gives us around 3 gigabytes to play with. So that's all a heap is. It's just a giant memory region. So we point at our heap address here, and we create a heap implementation that manages that heap memory, that giant chunk of memory. And that is what your heap is essentially. So for example, we could decide that we want a 100 megabyte heap. And as long as we have 100 megabytes of memory available to us, our heap will work absolutely fine. So we can't just have that giant memory region. We need to create a heap implementation that will make our heap work properly. It'll keep track of what's already allocated, what needs to be allocated, and so on. The heap will be responsible for storing information in our kernel. So if someone says, give me 50 bytes, we will find a memory address inside our heap region that's free, and we will give them that memory address and say you can use this memory address up to this size. Do not use more than this size. That's what we can do. They tell us they want 100 bytes of memory. We find 100 bytes of memory for them. That is what our heap implementation is for. So simply put, our heap implementation will be responsible for managing this giant chunk of memory that we call the heap. So the simplest possible heap implementation is rather simple. We find a start address, so we can point it at this address, for example. And then any call to malloc gets the current address, stores it in a temporary variable called temp, and now we increment the current address by the size provided to malloc. The temporary variable called temp that contains the allocated address is now returned. The current address now contains the next address for malloc to return when malloc is called again. So the benefits to this, it's incredibly easy to implement. There is no easier heap to make. The negatives, you can't actually release memory because we don't keep track of how the memory was allocated. Being unable to free the memory will lead to memory leaks and eventually a system crash. This is the C code for the simplest possible heap implementation. So we can see we have our current address. This points to that giant memory region that I was talking about. We then set a temp variable to the current address. We increment the current address by the size provided to us. The current address now points to the next memory region for the next person that calls malloc, right? And we now return temp, which is the address that we allocated. If you call malloc and say you want 50 bytes, it will return this address here, the one that we've written here. And then the next address will be this address plus 50, right? So the next person that calls malloc will get that address. And obviously our free function here can't do anything because unfortunately this heap implementation is far too simple for us to keep track and be able to free blocks. A very poor implementation indeed. Okay, so how will our heap implementation work? We obviously want something we can allocate and free from. Well, our heap implementation will consist of a giant table which will describe a free piece of memory in our system, right? That's how ours will work. So this table will be responsible for describing which memory is taken and which memory is free. We will call this the entry table throughout the rest of this presentation. So that only makes up part of our heap implementation. We also need a pointer to a giant piece of free memory. Again, that address that I showed you here, this address here will be where we will point that, right? And that'll give us around 3 gig of memory for a 4 gigabyte installed system. So yeah, simply put, this pointer will point to that memory and we will call this the data pool. If we set up our heap to be able to allocate 100 megabytes of RAM, then the heap data pool will be 100 megabytes in size, okay? Our heap implementation will be block based, so each address returned from malloc will be aligned to 4096 bytes and will at least be 4096 bytes in size. So for example, if you call malloc and request 50 bytes, it will give you 4096 bytes because that is the lowest block size we can give you for the memory you're asking for. So our entry table composes of an array of 1 byte values that represent an entry in our heap data pool. Array size is calculated by taking the heap data pool size and dividing it by our block size of 4096 bytes. We are then left with the total number of entries we need in our array. So for example, if you want a heap that can store 100 megabytes of data, then we do 100 megabytes divided by block size, in our case block size 4096, and that will give us 25,600 entries in our entry table. Because each entry is only 1 byte, that means our table will be 25,600 bytes in size. And this entire table will describe how the 100 megabytes is allocated and what is free in that heap data pool for us to allocate to someone else. If our heap data pool is at this address, then entry 0 in our table will represent the same address, this address here, 0x0100 and so on. Entry 0 in our table will represent that address. Entry 1 will represent the same address plus 4096 bytes. Entry 2 will represent entry 1's address plus 4096 bytes. So you can see how each entry is in charge of a 4096 block chunk. So as you know, each entry in our table is just 1 byte. So we need to use bitwise logic to allow us to make use of that memory efficiently. So the lower 4 bits in an entry in our table will represent the entry type. We can discuss that more later. The upper 4 bits are flags describing our entry. So bit 7 in our entry byte is has n, and has n is set if the entry to the right of us is part of the allocation. So for example, if we allocate entry 0 in our array, but it takes up 2 blocks, then entry 0 will have the has n flag set because block 1 will also be part of that allocation. If block 1 is the last block of that allocation, then its has n flag will not be set. Bit 6 in this byte is the is first. This is set if this is the first entry of our allocation. Using these 2 bits, it helps describe how we should be handling the memory. These 2 bits are very important because it describes how long an allocation is and when an allocation ends, which is essential for our heap. These 2 bits represented with 0 are not used. Each entry byte in our table describes 4096 bytes of data in the heap data pool. In my heap implementation, we only have two entry types. We have the entry taken and the entry free. If the entry is free, we can use it. If the entry type is taken, we cannot. The data pool is simply a raw flat array of thousands or millions of bytes that our heap implementation can give to people who need memory. Let's now discuss how we can create our own malloc. Firstly, we assume we set our heap data pool to point to this address, 0x1000 and so on. We assume our heap is 100 megabytes in size. We assume we have 25,600 entries in our entry table that describe our 100 megabyte of data in the data pool. As you know, this is calculated by taking the heap data size and divide it by our entry size of 4096, which gives us 25,600 entries that describe the 100 megabytes of memory. So the memory allocation process will seem complicated to you. However, this implementation can be written in less than 200 lines of code, so just bear with me. The first thing we do is we take the size from malloc and calculate how many blocks we need to allocate for this size. If the user asks for 5,000 bytes, we will need to allocate 8,192 bytes because our implementation works on 4,096 byte blocks. 8,192 bytes is 2 blocks. We now check the entry table for the first entry we can find that has a type of heap block table entry free, which means that the 4096 byte block of memory that this entry represents is free for us to use. Since we require 2 blocks, we also need to ensure the next entry is also free for use. Otherwise, we will need to discard the first block we found and look in our table until we find at least 2 blocks that are next to each other, because we need 2 blocks to allocate 5,000 bytes. Once we have 2 blocks, we mark those blocks as taken. We now return the absolute address that the starting block represents. The calculation is the heap data pool start address, i.e. 0x1000 so on, plus the block number multiplied by the block size. That is the absolute address we return that the programmer who called malloc can use. So let's break this down a little bit then. How do we find the total blocks? Well, we know our block size is 4096. So we get the size provided to malloc, for example, value 5000. We then align it to 4096. We then get the value 8192. This is the code for doing that. We use this modulus operator to get the remainder. Now we just divide 8192 by our block size of 4096. 8192 divided by 4096 gives us 2 blocks to allocate. So now that we know that, we need to find 2 blocks in our entry table that are free. Take this example entry table I've made that is actually based on the bit masks that I showed you previous in this presentation. So obviously these are the hexadecimal equivalents, so feel free to change them to binary to see how this lines up properly. So 0xC1 means the block is taken. This is also the first block for this allocation, and that this allocation has more blocks and is not finished. 0x41, the block is taken. This is the first block, but there's no more blocks for this allocation. 0x81, the block is taken. We have more blocks for this allocation. We are not the first block for this allocation. 0x01, the block is taken. We are not the first block for this allocation, and there are no more blocks for this allocation. 0x00, the block is free. However, we should always just check the lower 4 bits to see if it's free, because technically the upper flags could still be set, and this should still be legal because the lower 4 bits represent the type, and the type tells us if it's free or not. So here we can see that there's an allocation. 0xC1, what does this mean? Block taken. This is the first block, and we have more blocks for this allocation. So okay, so that tells us that, yeah? Now we see 0x81. What does 81 mean? Block taken, we have more blocks for this allocation. So we have 2 of those, and then we have a 0x01 which ends that allocation. So we can see that this allocation is 4 blocks in size. And it ends with 0x01, which has the 2 topmost flags as 0, which means that we are not the first block and there are no more blocks. However, because the type is 0x01, we are not a free block. But this basically means we're the last block. And you can see this goes on and on and on. Okay, so let's not get ahead of ourselves. We are looking to find 2 free blocks in the table. So there's 2 free blocks. We see 2 zeros. Remember, 0 means free. If the lower 4 bits are 0, the block is free. So we've found 2 free blocks. Brilliant. Let's allocate them. So we've now allocated them. We've set the first byte in red here to 0xC1, which means the block is taken. It is the first block of our allocation, and we also have more blocks for this allocation. And then we end it with a nice 0x01, which means this block is taken, we are not the first block, and there are no more blocks, which ends our allocation. So step 3, we now need to calculate the absolute address the programmer can use based on these blocks that we've calculated. So how do we do that? Well, know that entries in our table start from 0, just like in arrays. So the first highlighted byte, 0xC1, is at index 22 of our entry table, or our entry table array. So 22 multiplied by the block size of 4096 gives us 90,122 decimal. This is our offset. The heap data pool starts at address 0x010000 and so on. So all we do is we add the 90,122 decimal to that number, giving us an absolute address of 0x101600A. This is the absolute address our Malloc implementation has found for us. We now return that address, and the programmer can safely write our 5,000 bytes to that address. Technically, because it's allocated 8,192 bytes due to our 4,096 byte block size, we can use up to 8,192 bytes before overflowing into other people's memory. However, the program that used Malloc only wanted 5,000 bytes, so for him to use more than that, it probably means there's a bug in his program. So now let me explain how we can free. Well, we calculate the block number based on the address provided to us. We can get more on that later, it's not too difficult. We go through the entry table starting at the block number we have calculated and set each entry to 0x00 until we reach the last block of the allocation. And we know when we're at the last block of the allocation because it will not have the has_n bit set in the entry byte, which means that there's no more next to us for this allocation, right? There's no more blocks associated with this allocation. So what are the advantages of our implementation? It's fast to allocate blocks of memory. We're not relying on linked lists here. We're just setting indexes in an array. These can be calculated very quick on the processor because it's essentially just a multiplication. The size of the data type for our array multiplied by the index. It's not difficult. It's also fast to free blocks of memory for the same reason I just mentioned. We go back through the array, we set it to 0. It can be written in under 200 lines. This is easy to implement. I know it sounds complicated, but it's easy to implement. So the disadvantages of our implementation, we can allocate in memory blocks, meaning misaligned sizes. So for example, back to the 5,000 bytes situation, we have to give it another 1,500, 2,000 bytes for it to work in our implementation. Now obviously there's a lot of advantages to using block size heaps. They're faster, for example. But we do waste memory here. What modern operating systems tend to do is your user program will have an internal heap and it will ask the operating system for more memory for those bigger chunks, and then it will handle the memory in the user application using much smaller sized blocks or a better implementation that's suited for smaller memory blocks. That's usually how that works. Whereas the kernel heap will be using the block-sized implementation that I've described here. So another disadvantage of our implementation, memory fragmentation is possible. Now, the memory fragmentation is basically when we have enough free memory to allocate some memory for someone, but because of the way the memory is laid out, we can't actually give them the memory they're asking for. So for example, let's say we had a heap that could only have 4 blocks of memory, right? So let's say the first block is taken, the second block isn't, the third block is taken, and the fourth block isn't. Now we know there's 2 free blocks of memory, right? However, because they're not next to each other, we can't safely give it 1 block of memory because it will overflow and overwrite the block of memory that isn't ours. So that's the memory fragmentation, right? So you can help solve this problem by using paging. However, this works best in 64-bit implementations because people having 4 gigabytes of memory is very common. People having terabytes of memory is not very common. So 64-bit implementations, you can get around this memory fragmentation issue using paging. In our 32-bit protected mode kernel, it will be a little more tricky, so we probably won't cover getting around that. Okay, I hope that explains the heap that we will be implementing in our kernel.